As I said, let's first discuss so just before the break, I stated the main known results, and as you can tell, there's this big difference in what to expect between codimension 1 and higher codimension for the singularities of our area minimizers. So what is the key difference? Well, codimension 1 and higher. Well, firstly, we the starting point, as you'd expect to analyze singularities, is to study blowups around these singularities. So as many of you probably know, we have the monotonicity of mass ratios for area minimizers. In fact, this is true for any stationary barofold. We have, this is just in Euclidean ambient space. You need the extra exponential factor if you have the ambient Riemannian manifold. So this to the m is a monotone increasing in R. So here by this, this is this mass measure of T. And as I said, you have this extra exponential factor in the case where you're in an ambient manifold. So there's this monotonicity for the m-dimensional mass ratios. And this tells us that we can extract these tangent cones at any point. So at any and support current, there exists a tangent cone C at X, such that these blowups, so for some sequence of blowups, where here this is like the push forward under the homothetic rescaling map. So that's RK of T, where this map takes a Y to Y minus X over RK. So really, when you apply this kind of so it like zooms in onto a small ball around X, the radius RK, and kind of blows it up to the unit ball. So these converge weakly star to this cone C for some sequence scales. Okay, going to 0. And why do we call this C a tangent cone? Well, it's because it's invariant under homothetic rescalings and it has constant mass ratio. So we have the m-dimensional C at 0 is the m-dimensional density of T at X, which in particular exists again by monotonicity, where this is the limit as R goes to 0. These mass ratios. And this is identically, so the mass ratios of T are all the same and equal to this density, of C, are all the same and equal to the density of T at X. Okay, so we extract this tangent cone, and we now want to understand, we want to study these tangent cones. But notice that this C is it's dependent on the sequence, this blow up sequence that you take. So, but possibly, it's a big open question in general, uniqueness of or non-uniqueness of tangent cones. So when can you expect this thing to be unique and independent of the sequence? In general, it's not something you expect. But we have this stratification due to Almgren, which tells us that stratification, which tells us that for any k, any integer k between 0 and m, we take the kth stratum of T to be all the points in the support of T such that any tangent cone at this point splits off no more than a k-dimensional spline. Just bear with me, I'll explain exactly what I mean by this. So any tangent cone C to Tx is of the form C is up to rotation, of course, RL cross some C prime, where L is no bigger than K. So this is up to rotation. So essentially what this means is that, so the points in the Kth stratum are those that have no more than K dimensions of symmetry. So like the picture is really somehow you have something like this, where this here, this is your RL, and this, the cross section, so like this guy, is your C prime. So C prime encodes the asymmetry of your tangent cone. And this RL is all the like the directions in which you have symmetry. So okay, and so in fact, due to Almgren, that the Hausdorff dimension of the Kth stratum of T is no bigger than K. So essentially, the points with the most asymmetry are the most sparse somehow. So like you're less likely to see these points, right? So and notice that this so there's also the more quantitative stratification of Neighbor and Baltorta more recently. I'll come to this towards the end of the talk. So this is more relevant when it comes to trying to get some structural results for singularities. Okay, so the importance of this stratification of Almgren is that it tells you that that essentially, in order to get the dimension estimate, like this finer dimension estimate on the singularities, it's enough to just look at the points in the top few strata. So if, like, you know, say you expect this m-7 dimension estimate on the singular set in codimension 1, then you just have to estimate you just have to deal with the points in the, so you know that already everything from the m-7th stratum downwards has this dimension estimate, so we just have to make sure that we don't see any singularities in the strata above the m-7th one. So somehow our enemies are the points that have a lot of symmetry. Okay, another, yeah, and this is what shows us the problem between codimension 1 and higher codimension, because it turns out that in codimension, in higher codimension, you start seeing singular points that have flat tangent cones. This doesn't happen in codimension 1. So key difference. In codimension 1, there are no what are known as branch points, which are points with, or like flat singular points. Singular points with flat tangent cones. But in higher codimension, these exist. So an example of where you see a singular point with a flat tangent cone is already this example that I gave of the holomorphic subvariety in 2D. So it turns out that the tangent cone that you see, the only tangent cone that you see at the origin, is the flat plane W equals 0 with multiplicity 2. So you see this, so that's a branch point, but it's still a singular point there. And the reason for why in codimension 1 there are no branch points is because of this characterization I mentioned of codimension 1 area minimizers as boundaries of top dimensional Kachopoly sets. So this tells you that essentially locally around every point that has a flat. So if you start with a point that has a flat tangent cone, then locally around this point, you can ensure that the density remains close to a constant on the entire neighborhood. And this, then you can apply De Giorgi's epsilon regularity theorem, or Allard's epsilon regularity theorem, if that's what you're more familiar with. And that allowed you to conclude that actually such a point must be regular. So there are no flat singular points. Okay, and after that, so the next, so there's nothing, also something to note that in the integral setting, there is nothing in the m minus first stratum. So in fact, this guy is empty. So there are no points that split off there are no points with a tangent cone that splits off exactly an m minus 1 dimensional spine. And this is because if you had such a point, then the thing you're left with, so remember that if it splits off this m minus 1 dimensional spine, you're left with this one-dimensional cone that's asymmetric. But this has to be area minimizing. And we know we have a full classification of one-dimensional area minimizers. They have to be line, like a single line with a multiplicity. Otherwise, you have a better competitor. So this tells you that actually you can't have, there's nothing here. So like essentially, if you're hoping for the m minus 2 dimension estimate on the singular set, the only enemy are the flat singular points. To get the more refined m minus 7 dimension estimate of in codimension 1, it's a dimension reduction argument using the fact that there are no branch points. But yes, as you're probably aware, the fact that Almgren's big regularity paper was originally a 1700-page monograph, and even since then has only been sort of reduced down to this 1,000 or so page book. And then, okay, simplified by Delelis and Spadaro, but still several hundred pages in total. So it's really, there's a lot of work that goes into getting this, to treating these flat singular points. And this is what I'll talk about from now on. Okay, so, right, so how do we deal with these flat singular points? So the approach of Almgren and Delelis, Spadaro. Okay, so the first step is quite natural in general. So this problem of area minimizers is, we're minimizing a non-linear energy. So we want to study first the linearized problem, which in this setting is still somehow non-linear, but we study, yeah, so step 1, study what we call the linearized problem, in the sense that we want to sort of linearize the operator, the area functional. And this corresponds to, so we want to understand the regularity theory of what are known as multiple valued minimizing harmonic maps. Okay, so what are these? And why are these the guys you want to study? So they take, they act on, they're defined on some open subset of Rm, say, and they take values, this weird Q valued space. So here Q is some arbitrary fixed natural number. Right. So what are these Q valued maps? Well, they take values in the space of unordered Q tuples. So they look like kind of U of X is P, which is an ordered Q tuple vectors. So Pi is in Rn locally. So sorry. So at each point, we have this unordered Q tuple. So you can think of these maps as like they take Q values at once, which you can't decouple. And we have no, we don't care about permutations of these Q values. So really the toy model comes from these, again, these holomorphic subvarieties, because if you think about this example I said, so if you think about any sort of graph of like the complex square root function, say, you have these two branches, these two sheets, and you can't decouple them anywhere around the origin. So that would be an example of a two-valued map. So that's really what you should be kind of thinking about. So these are maps that take these Q values all at once, and that you can't really decouple these values, and you also don't care about how you commute these values. But yeah, as I suggested, this isn't so the space comes with a topology, which the kind of the distance between two Q tuples is really like you take the optimal say little L2 distance over all possible permutations. So you take the infimum over all possible permutations of this. And this topology, I mean, it's a very non-linear kind of space, this space of Q tuples, and it makes it hard to work with because of this non-linearity. So for example, you can't sum up two Q-valued functions because of this non-linear structure, and this creates a lot of problems. I mean, okay, you can embed this this space of Q tuples into some much larger Euclidean space, but with a bi-Lipschitz embedding, this was work of Armgren as well. And this is how, at least this is how Armgren got a lot of the properties of these minimizing Q-valued harmonic maps through this bi-Lipschitz embedding. You can also do this intrinsically. That's what Delellis and Spadaro showed, that these two things are equivalent. That it's a, yeah, but still not so much is understood about the exact kind of geometry of this space. Okay, and then it's a theorem, and yeah, kind of as you might expect, the reason why this this kind of graphical structure is natural for when studying our area minimizers is because of these examples we see with the branching behavior, where we have these multiple sheets that we can't decouple. So theorem due to Armgren, which states that for any such a minimizing Q-valued harmonic map U, for such a map U, we have the following dichotomy. So either U is Q copies of a classical harmonic map, identically, classical harmonic, or we have the following dimension estimate on the singular set, or the set of Q points of U. These are the points that U of X is Q, Y, for some Y. But this is at most m-2. So what this tells you is that either U is trivial, i.e. it like collapses into Q copies of really a classical harmonic guy, which these we understand very well, or we have this m-2 dimension estimate on the set of all the points where you, like all Q sheets somehow collapse together, but you expect that locally around these points, you know, you don't see identical collapsing into Q copies of a single guy. Otherwise, you'd be in the first scenario somehow. Right, and this kind of dichotomy is proven by a dimension reduction argument, kind of analogous to the one due to Federer in the codimension 1 setting for the singularities of area minimizers. And that's because you don't see these kind of branch points at the level of this for the linearized problem. So you can blow up around a singular point and you get a tangent function. And this tangent function turns out to be a homogeneous guy of some degree. And you can show that this, you can study the spine of this homogeneous guy, and it has to be somehow, if you're not in the first setting where all your Q sheets collapse, then this homogeneous guy has to split off some spine, and you can keep sort of iterating this, take iterated blow-ups and reduce yourself down to 2 dimensions and then understand what happens there. So it's kind of this sort of inductive argument, this dimension reduction thing. But okay. Right, so once we understand the linearized problem, now we want to use this for the nonlinear setting. So we want to somehow pass what we know from the linearized problem back to our setting of area minimizers. So what is the next step? So step 2, we do a contradiction argument. So, okay, so we suppose the dimension estimate fails. What does this mean? This means that we can extract a density point of some higher dimensional Hausdorff measure. So there exists a HM minus 2 plus alpha density point, X, which is also a singular point, and we can assume that it has some integer density Q, because it turns out that somehow the points with non-integer densities actually have a lot of asymmetry, so they're in one of these lower strata that we can estimate well. And also you can assume that this density point, because as I said, our enemy are these flat tangent cones, because again, the ones with the cones with the ones in the lower strata, we can again estimate well. So we can assume that this point has a flat tangent cone. Flat tangent cone, which is Q copies of some m-dimensional plane pi. And we may assume, so implicitly, these 2 criteria, the density point and the existence of the flat tangent cone, they come with sequences, right? So at least for the density point, you extract some sequence along which you see this positive m minus 2 plus alpha dimensional clustering. And for the other one, you see the sequence along which you get this cone. But it's actually not too much work to show that you can take the same sequence for both. So we may assume that both of these behavior are seen along the same sequence. Some sequence RK going down to 0. Right, and now we want to use these 2 things to get our contradiction. So what do? We want to approximate our surface, our m-dimensional area minimizer, by graphs. And these graphs have to be multiple valued. So, and because of this Q, with this density at this point, it means that locally around this point X that we take this density point, the graphs we expect take Q values. So we can approximate T around X at scales RK by Q valued graphs. And then the hope is we want to take a limit of these graphical approximations, and we want to take an appropriate limit, call it U, such that first U is a Q valued minimizing harmonic map. Also, we want U to be non-trivial. So not Q copies of a classical harmonic guy. So not the first case in this dichotomy. And finally, we want persistence of the singularities so we see around this density point of T, we see this higher dimensional clustering of the singularities. And we somehow want to pass this higher dimensional clustering through to the limit U to say that, oh, well, we've got this minimizing Q-valued harmonic map. It's non-trivial. So it's in the second case of this dichotomy we have for the linearized problem, but it has many, many singularities. And this can't happen because we know that we have the dimension estimate there. So that will be our contradiction. Singularities to U. Right, but this, okay, it sounds like, well, we're pretty much done, but actually it's very non-trivial to show all of this. I mean, this is where the hard work lies, achieving all of these properties for the limit. And you know, what's the first naive approach? Well, the first naive approach would be to build these graphical approximations over optimal planes. So build graphical approximations to these rescalings of T over optimal planes. But it turns out that this is a bad idea. Why is that? Well, consider the following example. So you take the surface induced by this two-dimensional holomorphic subvariety. The two is in real dimensional, not complex, coming from the following. So something like, say, this, right? And this is kind of like the graph W is like Z squared plus this very high order three-sheeted branching, right? But this is a problem because it turns out that if you approximate this with a three-valued, if you try to approximate this with a graph, which should be three-valued, then you try and you do this at all these blow-up scales and you try and take the limit, it turns out that unfortunately the limit just collapses to this, to see this Z squared term. So you don't capture this singular behavior. So it turns out that if you build this as a graph over the optimal plane, which would be, I guess, the plane W equals 0, then here the limit would be something like 3 multiplicity 3 Z squared, multiplicity 3 coming from the fact that we have 3 sheets. And this is bad, right? Because we lose this singular behavior. Our singularities have not persisted. And what we've got is actually this kind of average of the sheets, this Z squared. Like this is exactly, because if you think about it, this is like this three-sheeted graph built over the graph of Z squared. So it's like the Z squared is exactly the average of the sheets. And to fix this, we have to subtract this average of the sheets. So we subtract kind of this contribution coming from Z squared in this case. So how to fix this? Like I said, we subtract the average of the sheets. The Q sheets of T locally. And this average of the sheets locally is exactly what is essentially kind of the known as Armgren's center manifold. I mean, it's kind of like a smoothed average of the sheets. So I guess I should say subtract the smoothed average of the sheets. And then we want to instead build our graphical approximations over this center manifold, this average of the sheets. Call approximations over the center manifold. Okay, and we want to have regularity of this smoothed out average, this center manifold. And it turns out that we have regularity because it comes from elliptic estimates, because essentially these graphical approximations we get for our area minimizing surface have nearby harmonic approximations. And when we take the average of the sheets, it's kind of like they're close to being the average of the sheets of a multiple valued minimizing harmonic map, which is a classical harmonic map, and you have elliptic regularity there. So we get regularity for the center manifold via elliptic estimates. And actually, this is where this it turns out you need this C3 alpha regularity of the ambient manifold, because that's the only obstruction to that gives the obstruction of regularity for this center manifold. So you can get as much regularity as this the ambient space at best, and you need C3 alpha regularity for the center manifold in order to essentially you need this in order to bound various errors coming from variational estimates. Okay, so what we end up having is we have this sequence of graphical approximations, which we call MK, and they go from these center manifolds, these smoothed out averages MK, to this Q-valued space. Right, and these are our approximations. So now we need to show that now that we've subtracted this average of the sheets, we see persistence of singularities in the limit. So now I want to show that NK converges, it turns out, in L2 and W12 loc strongly to some a Q-valued minimizing harmonic map. And U is non-trivial. Okay, and U will be from actually this plane, this flat tangent cone. Okay, so and singularities persist to U now. So we have exactly what we want for our contradiction. Okay, and it turns out that we can indeed establish all of these things, and let me just briefly explain why. So the fact that that U is non-trivial, this comes from, so we need, here is when we need Armgren's frequency function. And this is what I will now explain. And actually, you can use the frequency function to also show persistence of the singularities. So the original argument of Armgren and Delelis and Spadaro, they used a careful capacitory argument to get this persistence of singularity. So kind of using the fact that there's like this incompatibility between knowing the dimension estimate for the singular set of the limit, but on the other hand, knowing that you have persistence at each scale, from the singularities of the surface to the singularities of the these graphical approximations over the center manifolds, and you do like a careful covering kind of argument to get a contradiction. But you can also use a somewhat more robust argument involves getting a lower bound on the frequency function, which I'll explain. And this is what's needed for to get this improved Minkowski bound. Okay, so what is the frequency function? So the definition, frequency function. So this is, so if we take, let's just do this for minimizers, so for minimizing harmonic maps. Harmonic map. Then the frequency of u around a point x at some scale r is the scaling invariant Dirichlet energy of u at scale r divided by the scaling invariant height of a sphere of radius r. There's Dirichlet energy over L2 height with scaling invariant. This can be written as r over 2 times the radial derivative of the logarithm of the scaling invariant height. So here HU, so this is exactly this guy in the denominator. It turns out that, so what is this frequency? It tells you at the scale r the dominant homogeneity of your map at that scale around this point. And it turns out that computation tells you that this frequency is monotone increasing in R, and it's constant equal to some value alpha, if and only if U is alpha homogeneous about X. So kind of at the level of these graphs, it works in the same way as like monotonicity of mass ratios tells you that these things are constant if and only if you have a cone. Whereas here, this frequency also has monotonicity, and it's constant if and only if you have a cone, which is an alpha homogeneous guy in this case. Okay, and it turns out that for these graphical approximations, you can still make sense of the frequency function. Okay, maybe you have to smooth it out a bit, and you have almost monotonicity. So not quite monotonicity, because these things are not quite area minimizing. These things, sorry, are not quite minimizing harmonic maps. But yeah, so, and this is what we need. So we still have almost monotonicity of the frequency for these NKs. So in the sense that K less than or equal to, you have some factor. So in the same way as you have when you have an ambient Riemannian manifold. No, maybe here it should be capital R. But yeah, anyway, you have, yeah, we still have some almost monotonicity here for the graphical approximations, but the problem is that this is at the level of each individual graphical approximation. But we have to keep changing them. So as you go down the scales, your average of the sheets, the center manifold, the domain, changes, and so do the graphical approximations. But it turns out that we can still rule out this sort of collapsing, this triviality of the limit by getting a uniform upper bound on the frequency. Because if you think about it, this is like saying having a uniform upper bound on the frequency is like saying you can't have an infinite order of collapsing. So we can get an upper uniform frequency bound on the NK, which tells us that U cannot be trivial. And also we can get a uniform, in fact, lower frequency bound. So this is in my, this is for the Minkowski estimate. Bound. And this tells us that, so this effectively, having this uniform lower frequency bound gives us in turn tells us something about how the L2 height scales because of this fact that this frequency is this radial derivative of the logarithm of the L2 height. So it tells us a scaling for the height. And this tells us that that in fact you get persistence of the singularities in a very robust way to the limit. So actually it tells us, it allows when I established the Minkowski dimension estimate, it tells us that actually the Hausdorff limit of the singular Q points of the blow-ups of the current really persist through to the singular Q points of this limiting harmonic map. And this is needed for the Minkowski bound because for the Minkowski bound, you need to take blow-ups of varying centers, because somehow the way this is argued is you reduce the question of getting a Minkowski dimension estimate to one of getting the Hausdorff dimension estimate. But in this simplification, you have to pay by considering blow-ups with varying centers. And yeah, you need this. Okay. Right. And then just one final thing I wanted to say. So that's basically all I wanted to say. That kind of concludes, because we now have what we want for the contradiction. Some key sort of difficulties with frequency function methods in this multiple valued setting is, so I guess some difficulties, because the Angren's frequency function has been used in recent years to study classical harmonic maps, just single valued, and solutions of elliptic PDE. But some difficulties with frequency function methods here that don't appear in those settings is that, I guess, two main difficulties is that one, we have no classification of frequency values. So we have no classification of possible homogeneities in general for in the nonlinear setting. And even in the linear setting, there's been work by Cromwell and Wickramasekera in linear setting. But this only tells us what happens up to HM-2 almost everywhere still. So in general, we don't know whether we even have a discrete spectrum of frequency values, because we're in this very nonlinear setting where, so unfortunately, spectral theory can't really be used, and that creates problems. And also, we have to, our graphical, as I already mentioned, our graphical approximations keep changing. So even though we can use a frequency function for each individual one, it's not so easy to actually relate what happens between these things, because somehow you'd like to sort of continuously vary the blow-up scale and use that to relate the graphical approximations. But this is kind of the same as asking for uniqueness of the flat tangent cone, and this isn't in general known. So you might have some scales where actually your surface isn't close to being flat at all, and so it's not so easy. You can't really relate the behavior in these like gaps in the scales where you don't know what's happening. Okay, that's basically what I had to say. Thank you for listening.